Hi guys, welcome to Learn Electronics Repair. Today we're going to take these parts we have here and build a really useful bit of test equipment. This is something you need if you're doing repair work for sure. And yet it's so simple to build. So what do we have? Well, we have two, in this case, broken meter leads, but any old meter leads will do. We have a bit of terminal block, a potentiometer, 500 ohm, a resistor, 39 ohm, and some sewing needles, plus this little thing here. Let me draw the circuit diagram of this and I'll explain what we have and what we're going to build today and why we need it. This simple little device is a variable constant current generator. This is just what you need for testing strings of LEDs if you have a string of LEDs, for example in LED Christmas lights. So with the values I'm using today, this will test up to 8 LEDs in a string. We can just increase the voltage bit, get up to 10 LEDs. I'll show you how to do that. And this variable current source will give us between 2 milliamps or thereabouts up to about 30 milliamps. And that's exactly the sort of current we need for testing these sort of LED strings. We can also use this for testing Zener diodes as well, so it's very good for that. And without doubt, there are other uses for this sort of device in repair work. So let's look at the schematic, and it's very simple. So we have an LM317. This was the device, the thing that looked like a transistor with 3 legs on. Okay. To use this as a constant current source, we need a resistor, and we connect the other end of the resistor to the adjust pin. So this pin on the LM317 is adjust, this is in, and this is out. Looking at the pin out, we can see that in is pin 3, adjust is pin 1, and out is pin 2. The current we get, the constant current, depends on the value of this resistor R. And there are online calculators where you can effectively put in whatever current you want. It will give you the value of R. But it's so simple to calculate this. I'm going to show you how to actually do it. And it's probably quicker than going to find the online calculator, to be honest. So the value of the resistor is 1.25. That's the reference voltage of this LM317 divided by the current that you want in amps, and that will give you the value of the resistor in ohms. Okay, so our current source, the lowest current we want is around 2 milliamps, the highest is around 30 milliamps. So to work out the value of this resistor, we just take 1.25 and we divide it by 30 milliamps, which is 0.03 amps, okay? And that will give us the resistance value. Let's just do that. 1.25. That's the reference voltage of the LM317. As I say, that is a constant. It will stay the same. And we divide that by 0.03 of an amp, okay? And you can see it comes to 41.6. So to get 30 milliamps, we need a resistor of 41.6 ohms. Well, that's not a standard value. Let's use a value close to that, the closest one of the standard values. And we should get a current around 30 milliamps. We don't need this to be exact. So the resistor we're going to use is a 39 ohm. That's the closest standard value to 41.6. So what current will that give us? Well, this is just as simple as that was. So the formula in this case is 1.25 divided by the resistance, and that equals the current. Resistance in ohms, current in amps. Okay. Actually, this is volts. It's a reference voltage, okay? Just in case you wondered where that came from. So let's see what current our 39 ohm resistor gives us. 1.25 divided by 39 is 32 milliamps. That's fine, that's close enough. So this resistor will give us 32 milliamps. That's the maximum current we're going to get out of our constant current source. But we want to make this adjustable. To reduce the current, we need to increase the value of the resistor. Okay, so we'll use this formula again, and we'll go for 2 milliamps. So 1.25 divided by 0.002, that's 2 milliamps, equals 625. Okay, I'm going to use a variable resistor, and we don't get 600 or thereabout ohm variable resistors, but we get 500 ohms. So if we put a 500 ohm in series with the 39, okay, LM317 in, adjust, and we put a variable resistor in here, and our 39 ohm, like so, out, in, 539. The maximum resistance we will get will be 539. If we adjust this to 0, it'll be 39. That's the minimum. Go this to the maximum, it'll be 539. So what current will that actually give us? Well, 1.25 as always, divided by 539. It gives us 2.3 milliamps. That's close enough for us. Okay, 2.3 milliamps. So that's the range of the current we'll have by adjusting the variable resistor. If we wanted 1 milliamp, for example, we can use a 1k resistor here, or we could even work that out. So if we wanted 1 milliamp, we would go 1.25 divided by 0.001 is 1250, or 1.25k. So if we put a 1k resistor here with our 39, we'll have something close to that. Let's have a look. So 1.25 divided by 1039, that's if we use a 1k resistor. Yeah, no, 1.2 milliamps. So I'm happy to have 2 milliamps as the minimum, but that's what a 1k resistor would give you there. So that's the circuit. This LM317 is a very common component, but at the end of this video I'm going to show you another way we can build this using a TL431. This is something you will find in almost any switch mode power supply. These little power packs you plug in the wall, anything like that. I'm sure you've got some faulty ones around, and in there you will almost certainly find this TL431, and we can use that as well. So we'll look at that at the end of this, but let's build and test this device. There are various ways we could build this. We could use a bit of Vero board if we like. I think the easiest probably is if we just glue the LM317 onto the back of the variable resistor. We can then fit the 39 ohms, and we've just got an in and an out. And that's all we really need. If you look at this variable resistor, you'll see the metal can isn't actually connected to any part of the resistor. We'll just double check that. From here, I'm on the metal can. Okay, obviously connected to the shaft. But if we go to any of these pins, yeah, there's no connection, there's no connection, there's no connection. That's because the wiper, which moves around the track, is on like a plastic former inside here, and the middle pin connects to the wiper, but this part of it doesn't connect to it. You can always check that. The reason I'm doing this is because on our LM317 we'll find that the metal tab is connected to the in pin, yeah, so there is voltage on this. If you don't like building it this way, you can do it another way. I'm going to do it this way. We could use some araldite or epoxy resin, but the quickest way I think is to use some hot snot glue, because this is not going to get hot during operation. The current is extremely low. And there it is. Okay, you can see that's all put together. Okay. So this is pin 3, this is in. I've actually cut the test lead, just short, so I can put this near to the power supply. I'm going to use my bench power supply and set it to 24 volts, but to be quite honest, you could use something like 3 PP3 batteries in series, giving you a 27. This is ideal to run from battery. Or a couple of 12 volt batteries in series, something like that. It doesn't have to be exactly 24, 24, 27, 30, it really doesn't matter. As long as the supply is over 24, you should be able to test these Christmas lights, for example, okay? So that goes there into pin 3. Pin 2, we can see, goes to the end of the variable resistor, then the wiper through the 39 ohm back to pin 1. And pin 1 is also the output, so this is the other end. So now we need to put some needle probes on here. And this is what the sewing needles were for, because we want to be able to pierce wires with these. Here then we have a pack of sewing needles, extremely sharp and narrow. This is what we want. So we'll take a couple of these. Now you could try to solder to these, but you may have difficulty doing that depending on the type of metal. So I'm going to use the terminal block to attach these to the meter probes. So the basic idea here is we insert this into here, we insert the needle at the other end. I'll cut this into 2 pieces obviously, one for the red lead and one for the black lead, and then we have our needle probes. The black lead is just intact, it's the original lead, so this just goes to the negative end of your power supply or your battery. There's no connection from here to this little circuit. This is purely in the positive supply, okay? So there's no Gran connection to here. Okay, so that worked very well. From what I can see, these are extremely sharp. Time will tell if they are resilient enough. Otherwise, I could either try soldering them or clamp them and maybe put some epoxy resin down here as well to hold them in place, assuming I have a good connection to start with. But we'll try this to see if these will do the job and keep on working for us. I have my meter here set to milliamps. So let's try this and see what happens. You can see the variable resistor down here connected to my bench power supply. I have the bench power supply set to 24 volts. So if we go onto volts range on the meter, okay, between these 2 probes we should see 24 volts basically. Let's have a look. I'll actually use these crocodile clip leads, it just gives me some hands free. So this is one end of the meter. And the other end from here. This is I can adjust the current in a moment without trying to hold this all together. So yeah, 23.46 volts. So we have the voltage there. Now let's put the multimeter onto current, so milliamps range. Okay, plug it into here. Milliamps, it's just showing me where to put the lead. And we have 3.4 milliamps. Yeah. So if I adjust this now, yeah, that's turning the current down. So the minimum 2.38, which is basically what we thought it would be, and the maximum should be 30, or just over 32, was it? 29.4. So it's close. It's close. Yeah, 30 milliamps basically. 2 milliamps, and anywhere in between. Okay, so I'm just hands in the way, but I'm just adjusting the control here. Okay, so we can now use this to test our Christmas lights in this occasion. Let's see if we can light up entire sets of 8. By doing this, it makes it very easy to find out where the fault is. I'll set it to 5 milliamps. That's a good enough current for LED testing, to be quite honest. Another main beauty of this is it's very good for battery powered operation, because when you're not using it, there's no current drawn on the battery, so this only draws from your batteries when you're actually using it. Let's try it. Okay, so we can see we have some LEDs here on this string of lights. This one isn't working, okay. That's the first one on a set of 8. The reason I know that is there's 1 wire coming in and 2 going out. The 2 that are going out One of them goes to the first in the next set of 8, so that's effectively the signal just down to the next set of 8, and the other one goes to the next one in this chain. Okay, so if we look at this one, we can see, follow it along here, goes to this LED, and this LED is also not working. So now we can actually test these LEDs together, and we can do this up to 8 LEDs with this tester. In fact, if I set it to 30 volts, we'll get up to 10. So we can say this is the first LED. We just stick our probe in. It's very sharp. It goes into the wire. We go the other side into the wire. Is the LED any good? Yes, it's lit up. So we can now go to the next one in the chain, which is here. What do we get? Well, the first one's lit up and the second one isn't, even though I'm measuring through this LED. So this LED is faulty, and if I change that one, I'll probably find that all the ones in the sequence of 8 actually work now. I did this on the previous video. I showed that, so we can see that will probably fix all 8 on this set. I won't do another repair on. You can see the previous video. I'll link it. But using this method, you could, for example, go from the input of the first LED in the chain to the output of the fourth. If the 4 light up, you know the fault isn't in that half. You can go to the other half, okay? If they don't light up, go to after the second one. We now know it's either one pair or the other. If the first pair light up, the fault's in the second pair. One more test and you'll know which of those 2 is faulty. So in 3 tests, you can actually test all 8 LEDs and come down to the faulty one if there is just one faulty. So that's why it makes this much quicker using these probes. I did this on the previous video. I repaired some of these and showed that and showed them working afterwards, so I won't do it again on this video, but I will talk about the alternative tester if you don't have an LM317 to hand. And here is the alternative version of this device you can build using the TL431. This requires 2 additional components to the version we've just seen, but it's still very simple to build and you shouldn't have any problem finding the parts to build this one, to be quite honest. We have in, okay, and we have an NPN transistor on this one. So we need a transistor. This is a resistor, R, and this is out, okay. The NPN transistor is not critical. Anything that will handle 30 milliamps, which isn't very much, will work just fine. I'm sure you can find something quite easily. But what you do need to bear in mind is the wattage. So if you were using something like a 40 volt supply and you want to use this at the maximum 30 milliamps, this transistor is going to dissipate about 1.2 watts. So you need something that can handle at least that. If you're using it at 24 volts, which is probably more likely, then it needs to be able to dissipate 720 milliwatts. So you need a transistor that can handle that sort of rating if you use it at 30 milliamps. If you're only using this at low current, it's much lower than that, okay? So we need the NPN transistor that can handle the wattage. We need a resistor, a base resistor. Good value for this is 680 ohms. Okay, and this is where we connect our TL431. Like so. And so. Okay. And that is our constant current source. The current depends on the value of this resistor. The formula is the same, but the reference voltage is different. So for the TL431, the reference voltage is 2.5 volts, whereas on our LM317 it was 1.25 volts. So the formula, again, to work out the current is 25 volts over I, the current you want in amps, equal R, okay, and 2.5 volts divided by R equals I. The quick and easy way, well, whatever resistors we use on the other one, because the voltage reference is twice as much, they're just twice as big. So to get the same that we use, you'd have a 1K potentiometer, and your resistor would be 78 ohms, which you probably can't get as a standard value, so you'd either use an 82 or you'd use 2 times 39 ohms in series. Okay, so that's how to do this with the TL431. The TL431, by the way, this is the cathode, this is anode, this is ref, this pin, and the pin out for the device. Okay, pins 1, 2 and 3, and this is ref, this is the anode, and this is the cathode. So there is our variable constant current source. I'm sure this is an extremely useful device and can be used in many ways during electronics repair work. One thing that comes to mind is if you want to put an enable on some chip that isn't getting enabled, to see if it works, that sort of thing, because you can set the voltage coming into this, which will be the enable voltage. You can set the current down to say 1 milliamp or whatever you want, depending on the pot you use. But I'm sure there's lots of other ways we can use this during our work. So you guys, what do you think? Yeah, can you think of some good applications for this little tester? It's so easy to build. And yeah, I'm sure there's plenty of ways we can use it. Okay, so let us all know in the comments below. Thanks for watching, and I hope you enjoyed that. I look forward to seeing you all soon on another Learn Electronics Repair video. Ciao for now, guys.